Back for Dr. Geisinger's Physics 4 class. We're in Chapter 30 now. It's continuing study of inductance. With a sort of a twist, you know from past studies that a current induces, let's say, a B field. For this geometry, something like that. So that this would be from Biot-Savart's law or Ampere's law. So that a time-dependent current then will produce a time-dependent B field, and we have that the time derivative of the B field is not zero, and we get from this Faraday's law, or from Faraday's law, we infer from this fact that an EMF is induced in nearby conductors. So that's a prospect here that this conductor, this current carrying conductor, producing this B field, which in turn induces an EMF in conductors, that this current will induce in itself, and it's in the conductor carry it another current, and you know from Lenz's law, the direction of that current would be in the opposite direction. So we will work toward and end up in this chapter with a self-inductance. Let's start then just looking at a model case, a loop, current carrying loop in one turns, having some current I1, producing then a B field B1, and a nearby loop within two turns, so that the flux and some cross-sectional area there, so that the flux through the second loop we get from the definition of flux, that would be B1 in the plane of the loop, dA in the simplest case, B1A. In any case, this will be then proportional to I1, the current producing this B field. For the magnetic flux through the all the turns, this is also proportional to I1. And this current I1 induces then an EMF in this set of loops N2. And the proportionality constant we call notations M2 1. It's induced into by current 1 through loop 1. And as it happens, we can solve then for M2 1 if instead the current originated in the second set of loops, we would get the induced EMF in the first set of loops, and we can use this, do that analysis to find this. And just define so that this is M1, 2, define this as M, the mutual inductance between the loops. So we have that the induced EMF in loops, the second set of loops from Faraday's law. Or see this. What if the loops were connected? Well, what if it were like that? And this suggests that the current will induce in the conductor carrying it another current. And that's what we find experimentally. This goes to a self-inductance, and we use a different letter for that, L, d-I-d-t, where this is the current in the one loop. Which is for a given set of loops, given the n set of loops. All right, let's look at a problem number 30.5 from the text. Yes, indeed, this one right here. Two toroidal solenoids are wound around the same form so that the magnetic field in one passes through the turns of the other. So we have something like just a toroid donut, N1 and N2 overlapping. When the current in solenoid, let's write down these numbers first. N1 is 720, N2 450. When the current in solenoid 1 is 6.6, so I1 is 6.6. The average flux through each turn of solenoid 2 is that many Webers. So 2 is 0.035 for these two together. What is the mutual inductance of the pair of solenoids? What is M? M is, write it either way, N1, P1, I2. It's that, but also N2, P2, I1. We have I1, so we'll use this right here, and phi2. So just put in these numbers. And what is that? 2.39 about that many henries. And for part B, we're asked when the current in solenoid 2, now we have that I2 is 2.5. What is the average flux through each turn in solenoid 1? So the 1, just solving from here, is looks like M I2 over N1, and since we have M now, 2.39, 2.5, 720. This will be approximately 0.0083